continue. Unfortunately, I need to be present also today on the faculty council, so we will finish a little bit early, and we need to be in time to to do something. So in the previous lectures we obtained Einstein tensor, and we will continue today. And the title of the next this lecture, or this maybe we proceed with the second one. So this is energy momentum tensor. Energy momentum tensor. So you can find the difference notation of this name of this tensor. Sometimes it's also called stress energy, or stress energy momentum tensor, like this. So what is the problem? We are ready, and we obtained everything in principle what we need to describe the geometrical properties of the space. In this, so we already know Christoffel symbols, curvature tensor, Ricci tensor, scalar curvature. So and all this object describe the curves or the properties of the space from one side. From another side, if we would like to build and to find the equation for gravity, again, from this idea that gravity corresponds to the curve of the space, and from another side, gravity created by objects which has a mass. So in this case, we need to clarify what is exactly and how we can describe the matter which we need to put in the space. And this is exactly can be described by energy momentum tensor. So this is which describes the matter. So we to formulate the problem. So what we need to include some object which characterize energy and momentum of the medium. So what is important also that we need to find this object not for one particle. For example, when we used before, when we was working in classical mechanics. For in classical mechanics, we could write the energy and momentum for one of the particle, as you can remember, this conservation law and like this. Now we need to work with, so and it means that before in classical mechanics, we used, and for us was much more important, the integral property of one particle. And this is exactly energy and impulse, momentum. Okay, in this case, we need to take into account the local. So you can write in your conspect that in classical mechanics or before, we could use the integral properties of one particle. And now we would like to take into account the local, it means differential properties of the medium. So it means that we need to build the object which consists the information about energy, momentum, density in unit volume. So, and it means, and we will see now that it's related with to the 10 values which will consist of this object which we now will build. So what it means in this case? In this case, for example, the energy conservation law, this tell us about change of the energy and in some volume. And this is flow of the energy through the boundary of this volume. It means that in differential case, we need to know the energy density. Energy density we will call it this letter, epsilon. And the energy density by definition, so the dimension of energy density, this is energy in divide on L cube, where L, as usual, we put this is scale of the space. Okay, so for example, this is erg divide on centimeter cube. Also, we need to clarify another value, and this is scalar, as we understand. We also need to clarify and include vector of energy flow. So of flux and of energy flux. Okay, energy flux, energy flux. So we will call it. Usually, it's called by letter S. This is vector. And what is this? So this is energy density multiply on v velocity. So if we will know all these two values, this energy density and energy flux, we can find principle and we can understand the change of energy in any part of the volume which pass through the unit time. This is a second, so this is, okay, we'll write like this, change of energy in any volume in unit time, okay. The second one, we also can clarify, understand the flux, the energy flux, through, so I will write everything, through the surface of such a volume. So I will schematically, I will write it, describe it a little bit later. What it means in this representation, what it means from the point of momentum conservation law in differential form. It means that we have a change of momentum in some volume, and this is the momentum flux through the boundary of this volume. So momentum flux we can call like this P. It's not enough, letters. So okay, P. So momentum flux. Momentum flux, we can clarify as energy density on V divide on C squared. If we will put the dimension to understand the dimension of momentum flux, so it's mv divide on L squared. So it's understandable that we have we want to understand, since we speak about differential form of the matter distribution, because we need to understand the matter distribution in the space exactly. So it means that we need to put all time, this divide on L cube, where L again, this is the scale of the space in the space. So now I will try to explain it geometrically. What it means. So it means that if we have, for example, some volume, let's write it, this volume in the space is a distribution of matter, and it's understandable that matter can be not a static, so but it can move, through this volume. Let's put this volume like this. Okay. So for example, we have some flux, some flow of the matter. Let's put it here: X, Y, Cartesian system Z, and so this is just to represent this volume like this, and we have some passing of the matter, some flux of the matter. And we can write it like this. So it's understandable that it can go like this in different directions, or for example like this. Or like this. So in any of these directions, through any side of this volume. So if we will speak about change of, for example, X component of momentum in a volume of this cube, they related not only with a matter which goes through X, through the square which is perpendicular of the case, for example, like this one. Okay, so it means that we need to take into account the flux of the matter also, and this component also through another part of this volume. So, and we need to take into account all of this. And the flux of this vectorial value through any orbitally oriented surface, we need to determine it with, since we have a three-dimensional space, 3 on 3, which is equal 9 components. So, and this exactly value, which we call stress tensor, why exactly the, this tensor, energy momentum tensor, sometimes called as a stress energy or stress energy momentum tensor. So we can clarify it, we can describe it using the stress tensor, sigma, alpha, beta. So what means the stress tensor? By definition, this is amount of amount of alpha component of momentum which goes through some unit volume and goes through the one of the surface of this volume which is perpendicular of some axis. So if we will write, for example, x, y, z as x beta or alpha or some indexes, so which is perpendicular to correspondent axis beta. So you can see here alpha component which goes through beta component, so opposite component which is perpendicular. In principle, this stress tensor consists of the information how matter goes through the volume. And as I put here, you can see that it can be a complicated motion of the matter. Why we need to take into account the differential properties of all of this. So finally, the stress or energy momentum tensor, energy momentum. I put even stress to, you know, to put all components which this tensor has a following form. So this is usually called letter T, and has two indexes. So it means that this is tensor of the second rank, and that it has a form as a epsilon, so energy density. After this, we need to put what we clarified here, vector of energy flux. So S divided on C. C, this is speed of light. Okay, please write C. This is speed of light. As usual, we are using this letter. And we divide on C that we would like to keep the right dimension. Also, we will put C divided S divided on C. And here just we put minus to correspond the signature of our metric which we are using. So this is minus sigma alpha beta. So like this. If we will describe, if you will write it with all components, for example, in Cartesian system, so we can write it's much more detailed form. This is epsilon, this is Sx, C, S, Y, C, S, Z, C. Here also S, X, C, S, Y, C, S, Z, C. So, and here we need to put corresponding stress tensor, component of the stress tensor. So this is sigma X, X, sigma minus X, Y, minus sigma X, Z, and others too. So it's we understand that if we have some symmetrical distribution and motion of the matter, in this case we even can succeed with some diagonal form of energy momentum tensor, minus sigma YY minus sigma YZ minus sigma ZX minus sigma ZY minus sigma ZZ. Okay, so this is all components of energy momentum tensor. So it looks not simple, but we will see that due to some fundamental property of universe, which we observe now, energy momentum tensor really became very simple. But in general case, again, this tensor of energy momentum consists information about everything, about energy density, about flux of the energy, and about the distribution of momentum corresponding to each surface of the volume which we have. So this picture demonstrated.
Sorry, can I ask a question?
Yes, of course.
So for this energy momentum tensor, we have that it's 1, 1 element, 1, 2, and 2, 1 is vector, and 2, 2 is another tensor. Or how this works?
This part, in principle, you just consider as, for example, t 0, 0, this is epsilon. Okay. If we put t 0, because if you consider this 0, 1, 2, 3, so t0 I, no, it's better to write okay, like this, alpha beta equal minus sigma alpha beta. So like this.
Okay.
Yes.
Okay, that's understandable.
Okay. So what is important is as well, why, you know, if one tensor inside another tensor, but what is important that because yes, the stress tensor, sometimes you can use it separately, just but this is understandable. This is tensor which represents the matrix 3 on 3. But tensor energy momentum stress tensor consists all information. So, and again, for us is important the point that when we all time tell the word tensor, so we all time remember that this value doesn't, so it's covariant through the passing to coordinate system. So for us, it's important. Unfortunately, we don't have time to, because of course tensor momentum energy stress tensor is an interesting object. So, but cosmology course, including general relativity, from my point of view, could be much larger than we have now. So not much larger than we have. So, and I even don't understand. I discovered it yesterday when I received the letter about when we will have an exam. And it looks like exam will be in the beginning of, not beginning, the beginning part of December. So, and it means that the semester became shorter. Can you explain me? Or we will work on Saturday additionally?
Possibly, yes. We already have some pairs on Saturdays. However,
because nobody didn't say me that we have such a kind of idea that we need to. Okay, I will investigate it. In any case, so this is what I would like to say about energy momentum tensor, and we will continue to work with it, of course. So we will for cosmology, which for us much more interesting, we will investigate how it will be from the point of cosmology. Now, since I have not enough time, I have only like 15 minutes. I need to jump after this in council. So I want to start with a much more I say delicious, I would like to say delicious point. This is to obtain Einstein equation. So let's write, okay, Einstein equation of gravity. Okay, I will write, because of course Einstein equation, sometimes when you say person, if you can say person to person, that so look about something about Einstein equation, some people can immediately to think that this is MC square. So, and sometimes you need to clarify that we speak about Einstein equation of gravity. Okay, so as I said to you before, we can obtain Einstein equation a different way. One of the, and it's much more, I would like to say heavy way, but important also, this is through action of the gravitational field and Hilbert-Einstein action and action of the matter, like this. But this is really long procedure, so we need to spend two lectures, and also we need to investigate something additionally. I prefer to use another way, which is, from my point of view, even much more, not much more, but physical, and simultaneously we will obtain the limiting case for the weak gravitational field. So the idea is such a way that we will start from Newtonian classical mechanic and to try to generalize this for the classical Newtonian mechanics. It means that we are working with a weak gravitational field. And we will try to generalize it for the strong gravitational field. So this is, I like this this way to obtain Einstein equation too, because it's enough elegant and quick. So, and at the end of this part of procedure, we will obtain the expression, and now the goal which we would like to put. Maybe I only will start to do with this. What is the problem? The problem is that when we are working in classical mechanics, we manipulate with a physical value which we call gravitational potential. Okay, phi gravitational potential, and this is classical mechanics. So it means Newtonian. Okay, when we describe gravitational field. If we know gravitational potential, we can obtain the gravitational force, as this is a derivative of gravitational potential. So when we are now, we understand, and due to this effect that we would like to generalize it for any reference system, and which will correspond to Bill's theory, which is a covariant like this. So we already understand that we need to use tensors, and one of the value, very important, this is metric tensor. So metric tensor, because after this, if we know metric and all components of the metric tensor, we can find everything what we want. So Christoffel symbols, Ricci tensor, curvature tensor, so everything, including principle, if we will need it, we will see that finally, yes, we will need Einstein tensor and including Einstein tensor. So it means that now we are playing not with a gravitational potential. It's only as a limiting case. We need to work with a metric tensor. And the main idea, and again, we understand if we would like to build some theory as a theory of gravity and to find the equation, we need to build in such a way that finally the equation which we will have and the theory which we will have will include also the result of classical mechanics. So the result of classical mechanics, including gravitational potential, should be as a limiting case of the general theory. Because it's understandable why, because we have a lot of observational things later which proved us that weak gravitational field, classical mechanics works. And from another side, we also don't want to destroy everything, because from the point of economy, it's not a good economy, I mean, even in the science. So all time we try to keep what we had before and to involve this in the next stage of the theory as a particular case. Doesn't mean that it should be like this and nature described exactly like this, but for us it's much more convenient. From this point of view, now we let's find the relations between metric tensor, which describe again, as we suspect, the general relativistic case, with non-relativistic value, which is related with classical mechanics, and this is gravitational potential. So, and we will use now we will remind the Lagrangian in special relativity, because you know the special relativity is also should be included, because special relativity, why it's called the special theory of relativity, because it's related only with a special coordinate system, which has an inertial coordinate system. But of course, it should be also involved in the theory. So in special relativity, Lagrangian, and you worked with this some previous lectures about electrodynamics like this. So I will remind that this is minus mc square. So it's a relativistic case, so we need to put 1 divide v square divide on c square. So this is for relativistic case, in general case of special relativity. So if we will consider the limit of the velocity, which is much less than velocity of the speed of light, so like this, we just consider this square root in series, limiting by the first terms. So what we will have? We will have minus mc square, and square root, it means 1, we will have 1 divide on v square divide 2c square. So if we will just multiply the first and the second term, so we will have minus mc square plus mv square divide on 2. Special relativity. Okay, so what it means? It means that this, when we speak about special relativity, it means that in this case we don't have a gravity. Okay, general relativity we will have a gravity, but if we don't have a gravity, it means, and you can see here that we don't have any summand which consists the information about gravity. So we can schematically to put here that this corresponds to phi equals 0. In classical mechanics, if we will consider otherwise the particle which are located in some gravitational field, is located in gravitational field phi. We can consider the case when phi less than 0, so it's negative. So we can put here minus Gm divided on R, as we know well. In this case, Lagrangian will have a form. So this is kinetic part minus and m multiplied on phi. So this, if we now will, construct, let's construct some, okay, let's construct now Lagrangian which take into account gravitational potential and also special relativity, but for non-relativistic case. So exactly this one, this part, this one. So if we will look on this expression and this expression, in principle, we can understand how we can construct together, to join together the part which is related with special relativity and the part which is related with the classical mechanics. So it's like a trick. So we can write like this. We will keep this minus mc squared, and it's as soon as we have the speed of light, we immediately understand that we are working with a relativistic case. This is special relativity or general relativity. In classical mechanics, we don't have a speed of light in general equation. So after this, we understand we need to keep the kinetic part, which is here and here. And after this, we also will keep the part from classical mechanics which are related with the potential, with the gravitational potential. So in this representation, we just can take outside of the parentheses MC, and we will have brackets MC, and we will have C minus V squared divide on to C plus phi divide on C. Okay. So now we can write, since we have already expression for Lagrangian, we can write the action. What is the action? Action, this is integral from Lagrangian by dt. So in principle, this is general determination of the action in classical mechanics, which we will use. And let's put here as a Lagrangian what we construct before. So we will write minus mc integral C minus V squared divided to C plus phi divided on C dt. So we also understand that this action should be invariant relative to inertial reference system, and it means that and we also have the invariant if we will write it from the other side, from the point of special relativity, the action we can write as a minus mc divide on ds, where ds, this is ds small. No, don't This is ds small. Where ds small, this is interval between two events, and in special relativity, let's write it here. In special relativity, ds square, as we know, this is okay. I think we will call this eta. I don't remember, eta ak dx I dx k, where at ik, this is 1 minus 1 minus 1 minus 1. Okay, here 0. And in general case, I will write general the square. This is so this is a general case where we have a metric tensor. So if we now compare this two representation of the action through this, you know, what we construct now, try to join together classical mechanics and expression through the potential, gravitational potential, and this one using the special relativity. So we understand that this ds will correspond this part. Okay. So, and in this case, we can write that ds square, the interval between two events, we can write as a c minus v square c 2c. Yes. Plus phi divided on c square dt square. And let's consider what is this. So we just need to make some manipulations. So v square 2c square dt square plus so this is square between two terms, square of the sum of two terms. So this it will be 2 phi divided on c, c minus v square to c dt square plus here phi square c square dt square. So you can rewrite, but I will use this one. So I will do like this. I will clean it because I'm lazy. And I will open these brackets. So it will be equal. So it will be c square dt square. Minus v square dt square. So and plus 4c square dt square. Okay, just open brackets and to consider all summoned. So now again I will remind that in the beginning when I even construct the Lagrangian, I consider the case when v divide on c much less than unity. So the velocity are not relativistic, but we are using in any case relativistic case, but the velocity is not relativistic. So, but we keep some general representation. It means that I don't care about the terms which has a power law higher than for example, v divide on c, or even squares. It means that I can kill this one almost 0 because it's this summand will be small. I also want to write here. You can rewrite, but I will put here. And here I will it will be what it will be here. It will be 2 phi dt square. So I rush, and I already a little bit concerned that I can make a mistake. So please check what I write. Phi v square divided on c square dt square plus, yes, and this I kill. Okay. Plus. Just I open brackets to have the sum and to work with this. So again, I can see that this is also, I can consider as a small value, and I don't care about this. And what I have, finally, I have, and I will put here like this, c square dt square. I will put in the front this one, 2 phi dt square. So what about this one? The last one, I also can consider as a 0 because it's divided on c square, and c square it's a big value. So finally, this term will be small. And this one, it will be exactly minus dl square, because L equal V multiplying T. Okay. So, and I see that I have to sum with dt square, so I can write this d is s square equal 1 plus 2 phi divided on c square, because I want to take out exactly the sum on c square dt square minus the L square. So if I will remind that in general case ds square represents through the metric tensor, I can immediately recognize that if we will put the notation that we will call as x0, this is coordinate st, and x1 x, x2 y, x3 z. So I can see that this 1 minus plus 2 phi divided on c square, this is 0 component of the metric tensor. So this is very important things which we obtain. So we obtain the expression for the 0 component of metric tensor through the Newtonian gravitational potential. In the limiting case, when we pass to the non-relativistic mechanics. And this already, this expression can tell us something, but unfortunately, I need to stop lecture for now, because I need to be present on the faculty council. So, but on the next lecture, we will, using this one, we will obtain Einstein equation, knowing this, what we obtain here. So if you don't have a equation, we can finish here. I'm sorry. Pronto? Per favore, tu puoi aspettare una minuta, perché io Yeah. Excuse me, just a second. Excuse me, please wait for a second. Sì, non capito, questo è bit? No, io non lavora adesso, adesso io so excuse me, are you here?
Yes.
Yes.
Actually, can I ask you a question
Yeah.
about the tensor energy momentum that you wrote at a previous slide?
Mhm.
And as I understand, that components like minus, sigma, xx, xy, and so on, they are dimensional, or I don't know how to describe it.
Yes, yes, and this tensor also dimension as a dimension. So the dimension of this tensor, we can put it here. This is, as you can see, should be dimension of energy density, and this is energy divide on L cube. So, and all time. Huh? Sorry.
Okay. I just need some time to understand all this, because it's hard.
In principle, this, for example, can be dimension of the pressure. So we will see when we will apply it in some special case. For example, when we will speak about possible representation of tensor energy momentum tensor for models of universe and about distribution of matter in the universe, you will see that in principle this part we can represent and this stress tensor we can represent through the pressure. Of course, you need to take into account the speed of light because we want to keep the dimension which should be the same as the energy density. So this part we can represent through the pressure. But we will come back to this and just a second. And so later we will also consider the case for some examples. Okay. Did I give the answer on your question?
Yes, I think yes. Thank you.
Okay. Just a second, I need to make a screen your presence. No, any question?
Maybe no, but it's hard to understand why sigma is has minus. Yes.
Okay. In principle, this is also related with the signature. So we can speak now. I need to rush really, so I will quickly to make. Just a second. Okay. Again, somebody with K with a more complicated representation. I don't know what is this. So in principle, we have representation, as you remember, also with from one point we have a signature, as you remember from previous representation of interval, which is also have a signature plus and minus. From another side, to have to satisfy is momentum conservation and energy conservation. So it should be coincide with the law for conservation. So and why we have a minus here? But if in principle we can consider it much more in detail in the next lecture. Now, sorry, I need to leave you. So yes, and see you on Monday. So if nothing will be happen, so we will see each other on Monday. So thank you very much, and collect your questions for the next lecture. Okay.
Okay. Thank you. Goodbye.
Goodbye.
Oh.